Hello, and welcome to Lesson 5 of this Introduction to Differential Equations with Wolfram U. The topic of this lesson will be linear first-order differential equations, methods of solving these types of equations with constant and non-constant coefficients, and the integrating factor method. Let's begin with a brief overview of this lesson. The first class of differential equations that we will study in this course is first-order linear differential equations. These are differential equations of the form given here, where p of x and q of x are arbitrary functions of x, while y of x is the function we are trying to find a solution for. In the special case where p of x and q of x are constants, the terms involving x and y of x can be separated, and integration can be used to find an expression involving the solution. For an arbitrary first-order linear ODE, where p of x and q of x are not constant, the integrating factor method of Leibniz can be used. Both of these techniques will be discussed in this lesson. We will begin with the case of constant coefficients. Here we have a first-order linear differential equation where our p of x term equals the constant a, and our q of x term equals the constant b. Assuming that a is not equal to 0, divide the equation by a and rewrite it in a slightly different form given here. Since y prime is equal to dy over dx, move dx over to the right-hand side and integrate. For the left-hand side, the function y of x itself will be the variable of integration, and 1 over y of x minus b over a will be the integrand. For the right-hand side, minus a will be the integrand, and the variable of integration will be x. We're also using the generated parameters option to generate the constant of integration seen in the solution. We'll see shortly that these constants of integration are important when solving the initial value problem. Now that we have an expression involving y of x, solve that expression for y of x to obtain the general solution. We can clean the solution up a little bit by defining e to the c1 as just another arbitrary constant, c. With this definition, we have our general solution to the first-order differential equation with constant coefficients. Now, it is always important to verify a solution by substituting it back into the differential equation to confirm that the solution satisfies the equation, and we can see that it does. This is an example of using the separation of variables technique, which we will discuss in more detail later in this course. Let's use our general solution from the previous slide to solve a particular equation. Here we have a first-order linear differential equation where the p of x term is equal to minus 5 and the q of x term is equal to minus 2. The initial condition states that the solution equals 5 when x equals 0. We can use the result derived on the previous slide and replace a and b with their respective values to write the general solution for the problem. To apply the initial condition, evaluate the general solution at x equals 0 and set this result equal to 5. Now that we have set up the equation, use solve to solve the resulting equation for the constant c. We can see that when c is equal to minus 23, the general solution will satisfy the initial condition. Therefore, we can write the solution to this initial value problem by using c is equal to minus 23 in the general result. It is often useful to compare the solution to the initial value problem with the direction field. We can see that the solution satisfies the initial condition at x equals 0. It rises slowly at first as indicated by the arrows, but as y increases, the rate of increase of y goes up as well. This is caused by the exponential term seen in the solution. The method we have just discussed does not work in the general case where the coefficients are not constant. When this is the case, the equation must be multiplied by an integrating factor, which allows the left-hand side of the equation to be written as the derivative of a term involving y of x. Through the integrating factor method, it is possible to solve many first-order linear differential equations. Consider the general form for a linear first-order differential equation with non-constant coefficients. As a first step in solving this differential equation, multiply it by an unknown function mu of x, known as the integrating factor. Doing so puts the equation into this form. The point of multiplying by mu of x may not be obvious until we consider the derivative of mu of x times y of x using the product rule from calculus. We can see that the first term, mu of x times y prime of x, is already identical with the first term on the left-hand side of the differential equation after we multiplied by mu of x. The second term is identical if mu prime of x is equal to mu of x times p of x. Therefore, if we can find a mu of x that satisfies this auxiliary equation, we have found the integrating factor, and we can use it to solve the differential equation. We are looking for a function mu of x, which, when differentiated, gives the function itself back multiplied by another function. This is indicated by the auxiliary equation. Therefore, a good guess at the form of the integrating factor is e to the x, since the derivative of this function is the function itself. In order to get the p of x term in the auxiliary equation, assume that the exponent contains not x, but an arbitrary function of x, which we will denote by f of x. Calculate the derivative of this expression to get a relation between f of x and p of x. Notice that this result satisfies the auxiliary equation when p of x equals f prime of x. Therefore, we can use integration to calculate f of x and write an expression for mu of x given here. This satisfies the auxiliary equation since the derivative of mu of x gives the function itself back times p of x. With e to the integral of p of x as the integrating factor, the differential equation can now be written in this form. The left-hand side of the differential equation was previously shown to equal the derivative of mu of x times y of x. Using e to the integral of p of x for mu of x, we can rewrite the differential equation in this form. This and the last equation on the previous slide can be shown to be the same using the product rule from calculus. Now we can integrate both sides with respect to x to obtain the equation here. Solving for y of x gives the general solution. Since p of x and q of x are given in the differential equation, we know all the terms on the right-hand side, so we can find an expression for the solution as long as the integrals exist. Let's use the integrating factor method to solve a particular first-order differential equation with non-constant coefficients. Consider this first-order differential equation, where the p of x term equals 1 over x and the q of x term equals sine of x. The initial condition says that the solution should equal 0 at x equals pi. First, define the function p of x and q of x in the Wolfram language. Then, use p of x to calculate the integrating factor. Now that we have the integrating factor, we can use the general formula that we derived in the previous slide to calculate the general solution. We can confirm the solution by comparing with d-solve value. It can be seen that the solutions are indeed identical. Now that we have the general solution, solve for C1 using the condition that the solution must equal 0 at x equals pi. We can see that the general solution satisfies the condition when C1 equals pi. Now let's compare the solution with the direction field for this differential equation. The solution we found to this problem follows the direction field well and satisfies the condition at x equals pi. Consider another first-order differential equation with an initial condition. In order to define the p of x and q of x terms, the y prime term must have the coefficient of 1. Therefore, divide the equation by x, then define the p of x and q of x functions in the Wolfram language. Now that we have these functions defined, we can use the definition of the p of x function to define the integrating factor. Once we have the integrating factor found, we can use the general formula that we found previously to calculate the general solution. This general solution agrees with the result obtained from d-solve value, and we can see that these two solutions are indeed identical. Now that we have the general solution, let's solve the initial value problem. Use the condition that the solution equals 30 at x equals 1 to find the constant C1. The solution to the initial value problem is found by substituting this value for the constant in the general solution. Let's take a look at the direction field and compare it with the solution we found. It can be seen that the solution satisfies the condition at x equals 1, drops quickly as indicated by the arrows, but eventually reaches a minimum and rises again for larger values of x. This all agrees well with the behavior of the direction field. In this lesson, we discuss solving first-order linear differential equations, which take the general form given here. When the coefficients are constant, the solution takes a simple form, which can be found through integration. With the integrating factor method, linear first-order ODEs with non-constant coefficients can be solved using a general formula. This formula can give a symbolic solution to an arbitrary first-order linear ODE, provided the integrals in the expression exist.